All right, so let's go ahead and get started. So a couple of first pre-class announcements as per usual. First thing is I just posted two homeworks onto Blackboard. You want me to do, I keep on forgetting if y'all's class is the Monday or Tuesday due date, but whatever it says on Blackboard, it's either Monday or Tuesday, 5 p.m. It's going to cover a little bit about what we've done in the past week and what we're going to cover today and tomorrow. Other thing to talk about, I'll send an email about this as well. We had to start thinking about when our first exam will be. Do y'all prefer Wednesday or y'all prefer Thursday of next week? Thursday, that's what I thought. But I thought to ask. I will be posting some stuff like study guides and stuff like that, and access to old exams that I've done before. Again, I do want to emphasize whenever you look at the old exams from previous semesters, I want to emphasize that not everyone is going to be the same. Some of them might be really long, some of them might be really short. And that's largely due to the scheduling. For example, I think there's one that has 25 questions, but that's also because it was a 2 hour long exam. They met twice a week for 2 hours instead of 4 times once an hour, 1 hour. And then there's other ones that are really short, that might be like 5 questions. I'll change it up. I haven't decided on how many questions I'll give y'all. A couple of things that I do want to also note on how I make my exams. So the way that I usually make the exam is I make however many questions I think might be appropriate. I have randomized the numbers, and then I take the exam myself. So the first question I always like to ask students, just to get a frame of reference, how long do you think it should take me to finish my own exam with randomized numbers? And this with me writing out every single step. What do you think would have been appropriate? Well, let's say I make any exam. I made an exam for Cal 1 for exam 1. How long do you think it should take for me personally to finish an exam that I wrote? Again, I'll go with randomized numbers and showing every single step. So I'll tell you about how I usually do my balancing and try to make sure that the test isn't too long. I make the exam and then I take the exam myself where I write every single step. So it's not me just looking at it and be like, the answer is 5. It's me writing it out as if I was taking it. I time myself, and usually for this class, I aim for under 10 minutes, maybe 8 minutes. Because I say, I take my time, multiply it. I think for this class, my benchmark is times 5, maybe sometimes times 6. So in other words, if I can complete it in 8, maybe 7 to 10 minutes, is something I'm hoping y'all can complete within 50 minutes. So that's how I try to do a little bit of balance. So I don't necessarily always do, it's going to be this number of questions. I see, I'm making a preliminary exam, test it out, and then go from there. That way, that's how I sort of make sure that the exam isn't too long or anything like that. I think, for example, whenever I teach algebra, college algebra, or here pre-cal algebra, usually I aim to finish my own exam within 5 minutes, and then I give them, they should be able to finish it times 10, for example. So that's a little bit about how I do the balancing. Other things, for the exam next Thursday that we are planning, you are allowed to bring a calculator. The only exception about calculators is that it has to be a regular calculator. It cannot be your phone calculator. It cannot be your Apple Watch or anything like that. The rule of thumb is if it can connect to the internet or have Bluetooth access, it's a no. I don't care that if on your phone you say I can put on airplane mode. We're not going to kid around. We know it just takes 2 swipes to turn off airplane mode. So you can use a 4-function calculator that just has plus, minus, divide. You can use a TI-83, 84, any scientific calculator, graphing calculators. The big thing is to make sure that you know how to use a calculator. I highly recommend that whatever you use, that you know how to turn it on, you know how to set up the addition, subtraction, all that stuff. If you forget your calculator, I will not have any calculators to spare. So is the test doable without a calculator? For sure, but I would imagine that many of y'all would be more comfortable having the calculator, just as, you know, an option there. So I do recommend that you do remember to bring a calculator, make sure the batteries are charged and everything like that. Other things that whenever I give out the exam, it starts right on the dot at 5, and then I pick up everything at 5:50. So if you come in late, for example, let's say you came in at 5:40, it means you have 10 minutes to complete the exam. So I highly recommend that you come on time. I'll put this all in email just so that everyone knows, so that you can keep track of everything. The last thing that may be of interest to y'all is for the exam, you are allowed to bring a small note card, 3 inches by 5 inches. Emphasis on inches, not 3 feet by 5 feet, meters, anything like that. If you don't have a note card, I can start bringing some starting tomorrow, where you can see how large of a note card. It's not that big, maybe this big. Whatever you want to write on that note card, you are free to write whatever. If you want to write down examples, if you want to write down a theorem, if you just want to write down a message to yourself, if you want to write down all of the notes on a tiny little note card, by all means. If you can fit it on there, then you can. My only restriction is obviously 3 inches by 5 inches. Standard note card, no funny tricks, not a note card that folds out or anything like that. Yes, double-sided. And it has to be handwritten. In other words, you cannot put it into a printer and pop out size 2 font on it. So handwritten 3 by 5 inch note card. I'm not going to be checking what you put on there. It's whatever you want. So some people like putting examples, like I said. Some people like try putting all of their notes. Do try to be smart with what you put on your note card. Remember, the exam is only a 50-minute thing, so you're not going to have the entire time to read through all of your notes on a note card. So try to be mindful and be smart about what you put on there. For this exam, it might not be as useful, but you can imagine whenever we get into chapter 2 about the derivative, and we have 30 different derivative rules, then it's going to be really nice to have. And so those are some quick things about that. Any preliminary questions about, when our exam that's going to come up next Thursday? Again, I still haven't made it, so I can't say anything about questions. I think my plan is that this week we'll finish this section, and then Monday, we might move on to a new lecture on Monday, but then at least one day we'll do review, and then for y'all to ask questions and stuff like that. All right, sounds great. Let's go ahead and move into our lecture for today. As you might notice, I have a PowerPoint for today. This is not going to be very common, but I did this for some visuals that we're going to need to use here on how do we talk about the derivative. All right, so the first thing I'm going to go ahead and talk about for the derivative, well, before I even talk about the derivative, does anyone remember what is slope from algebra? I'm hearing a lot of different things, all correct. So some words that come to mind for me for slope: rate of change, rise over run, y2 minus y1 over x2 minus x1. Or if you had someone that was a little bit fancier, delta y over delta x, change in y over change in x. And whenever I talked about slope, what types of graphs was I looking at? Linear, so basically straight lines, right? So we're going to see how does slope and rate of change correspond to our calculus. So let's go ahead and start off with this here. Again, this is recalling what slope is. You don't have to write this because it is review. So if I give you a line, we know how to get slope. You have 2 points, whatever they are, and then you get slope is rise over run, or in other words, y2 minus y1 over x2 over x1, that is delta x over delta y. And while we're at it, just as a side note, let's see how much you remember from algebra. How did you get the equation of a line if you had slope and a point? Yeah, so if I gave you a point and a slope, you knew that you can make the equation of a line specifically from y minus y1 equal to your slope, x minus x1. So this is what we did, well, not maybe we, but what you did in algebra. How do you get the equation of a line? how we got slope, and everything like that. So we know how to deal with slope of a linear function. We know this because the rate of change is constant. It's always going up and over at a constant rate. So then the question becomes, in calculus, what if I had a little bit more of a weird looking function? We know that not every function is a straight line. For example, what if I had a function that just looks something like this? I'm going to draw over this. What if I had something that was a curved function like that? And then I said, find me the slope. Well, you would probably just say, well, that doesn't make sense. Slope is for straight lines. Well, this is what we're going to build up into is essentially, broadly speaking, how do I get the slope of a line that's not just a straight function, not a linear equation? All right, so let's see, how do we work around with that? So I'm going to introduce this definition. A good portion of today is just going to be listening and seeing how can we visualize this in our head. So here I have clearly a curved function. It's not linear. It's not a straight line. So suppose I choose a point on here. I'm going to fix a point. I know a point is an x comma y. Or if I have a function, my x comma f of x. Or in this case, I'm using the letter a comma f of a. I have some point that I'm fixing there. And then I might have a second point. Again, instead of using x2, y2, I can use x comma f of x because I'm dealing with a function, for example. Well, we know that if I have 2 points, I can always draw a line connecting the two. This is an axiom. If you have 2 points, there exists a line that you can use to connect the two. You can demonstrate that with a piece of string, for example. So again, you don't have to write this part because we're not really at the full definition yet. Even though I called it a f of a, x f of x, it's still 2 points in the long run. If I want y1, x2, y2. And then the slope of this line was, again, y2 minus y1, x2 minus x1. Again, you do not have to write this. This is a review on how do we get slope. If I want to be exact, this line I drew was called a secant line, meaning it hits my graph at 2 specific points. So this is how we generally got the slope of a secant line. Or if we want to be more broad, our average rate of change. So we have this, again, a little bit of a recap on what a secant line is and how do you get slope of a line. But instead of y2, y1, x2, x1, we're using f of x, f of a, x, and a. Does anyone remember what was the name of a line that touched my graph at 1 point? It was called a tangent line. So we have the slope of a secant line. How do I get the slope of a tangent line? Is what we're going to try to build up here. So let's see, how do I possibly get the slope of a tangent line? We know how to draw a tangent line because I have a point and I draw something that looks like it only touches the graph specifically at that point, generally speaking. So again, let me fix my point a comma f of a and some other point x comma f of x. This is the line I drew before. So somehow I want to build this and change it into a tangent line. So instead of touching twice, I want to turn it so it touches it once. So the question is, how am I going to do that? Well, this was one line. What if I choose a point that's a little bit closer? If I choose another point, I can draw a second line and do the same thing, right? This is still a secant line. And I can continue to do this. If I want to choose a point that's even closer, let's see if I drew that. I can choose one that's a little bit closer and draw another secant line. So again, I'm keeping this point here, and I'm seeing what's happening as I choose points closer and closer to my original point. What's happening with the lines, it looks like. Yeah, it looks like it's becoming a little bit like less steep. It's becoming flatter as I go closer and closer. What do you think would happen if I chose a point that's even closer? Let's say, oops, that's not what I want to do. Bring that back. Let's say I chose a point that is much closer, like right here. If I drew another line, again, you can probably expect I'm going to get a slope that's even flatter. So as I bring my points closer and closer together, my line looks like it's getting a little bit flatter here. Well, we have a little bit of this concept, right? Where we're getting closer and bringing numbers closer and closer together. That's what we called our limit, right? Our limit was we were taking x's and we were making them closer together. Well, that's what we're doing here. I have one value here. My x is getting closer and closer each time. So theoretically, we can go ahead and get as close as we need until we create a tangent line. That is, I could create a tangent line. Let's see if I animated it or not. Not yet. So I could get closer and closer, and it looks like for this graph, eventually I'm going to end up with a tangent line that looks a little bit like that, right? Where it's completely flat. So what I'm going to do is to get the slope of this tangent line, I'm going to go ahead and actually take the limit of the slope function. Because right here, this is the slope, right? y2 minus y1 over x2 minus x1. Here, we're going to see what happens whenever I take the limit as I take the points and they get closer and closer together. So again, we've done the slope, we've translated it to be in terms of functions, and now we took the limit where these points, x approaches a, that is, I choose my 2 points to be sufficiently close together. I claim that this will give me the slope of my tangent line. Not even claiming here, I'm defining this to be the slope of my tangent line. In other words, I'm finding the slope at this particular point A. So here I have A comma f of A. I can find the slope at that exact point. That is the instantaneous slope or instantaneous rate of change. All right, so we have this here. And this next part you don't have to write because this, again, a recap of what we're a little bit familiar with. If I have slope, I can make the equation of a linear equation. That is, if I want the equation of a line, it's still y minus y2, y minus y1 equal to slope x minus my x value. So even though we're using different notation, in the end, we're still using that concept from algebra. This time we just took the limit of the slope function. It's the big difference. And of course, the different letterings here and there. All right, so we have this here. Any questions about what I'm defining here to be the instantaneous rate of change? That's the slope of the tangent line. As a side note, one thing you're going to hear a lot from me for today's lecture and probably for the rest of Cal 1, whenever y'all were in algebra, y'all use slope and rate of change pretty much interchangeably. They meant essentially the same thing. What we're going to do here, let me save that comment until we actually introduce our other definition actually. All right, so I have slope of the tangent line. Don't worry about this example here yet. All right, so that's whenever I took 2 points and I made them closer and closer. Now, let me modify that definition a little bit further. But again, it's still going to be based in the slope. Again, I have my point A comma f of A. I haven't changed that at all. If I choose my second point, let's say it's h units over, arbitrary h. Well, if this is h units over, would you agree that the x value here is just a plus h? So here we have a plus h. This was a, and I moved h over. So this is why I'm getting a plus h. And then the y value is just plugging in a plus h. So again, I still have an x value. I still have a y value. I'm going to take a pause here to make sure. Any questions about where I'm getting a plus h?
So is h the representation of the y and the x? In a situation like this,
So h is representing basically our change in x.
the change in x.
And then this is just basically whatever the corresponding y value might be. Kind of like what we might have 3 and then 3 comma f of 3, or and then 4 comma f of 4. So this is just whatever y value corresponds to it. So really the big thing that's changing here is x plus h. Instead of calling it a random x, I'm calling it whatever this value was, moved h units over to the right possibly.
Wait, but doesn't that mean h in this scenario has two different values at the same time? Like where a plus h is the change in the x-axis, and then a plus h that's not in the function is the change in the y-axis.
So the h is a change in the x-axis from one to another, right? Because here I started a, the difference from a and a plus h, that's just h. That's how far apart they are. These f values, f of a and f of a plus h, do not necessarily have that same relationship. These are just, I have a function, I plugged in a, I plugged in a plus h. So the only thing that's really representing our change is h is the change from the first x to the second x. All right, so even though I've renamed them, there's still 2 points, right? x1, y1, x2, y2. So I still could use my slope formula. If I connected these with a line, I can find the slope of that line because we have y2 minus the first y. On the bottom, I do also have x2 minus x1, but it doesn't look like that initially. Where did I get h from? Yeah, look at what happens. x2, I get a plus h. So x2, so we're still doing x2 minus x1 down here. The first one is a plus h. My first x value was a. What happens whenever I clean this up? A plus h minus a. It just becomes a plain h here. So this is where my h is coming from. Or if you use the other definition before, where this is the change in y, change in x, the distance from my axis, that's a difference of h. We could also view it from that point of view. So again, even though it looks a little different, it is still y2 minus y1 over x2 minus x1. We've just renamed our variables to different ones. So first off, would we agree that this is a secant line? It hits my graph twice. Now, what happens if I want these 2 points to get closer and closer? Well, if these 2 points, I fix this point and I bring this closer, what's happening to h as I bring this closer? Yeah, h is getting smaller, right? The difference between my x's is getting smaller. In other words, h is getting smaller, that is, it's going to 0. So this was the slope of the secant line. What do you think is going to be different for the slope of the tangent line? It's going to be a limit. Just like before, we had secant line was just the slope formula, and then the tangent line, we took the limit. We're going to do the same thing here. So, like I said, we can make h smaller and smaller until h goes off to 0. This will give me the slope of the tangent line, which is the limit of this expression, f of a plus h minus f of a all over h.
So the limit of the average
Yes. In this case, we take the limit as h goes off to 0 because we're shortening our distances. Yes. So great. We have the instantaneous rate of change or the slope of the tangent line. It is this formula. The limit as h goes off to 0 of f of a plus h minus f of a all over h. And some preliminary stuff is that you can see I can't just plug in 0 for h. We definitely can't do that because on the bottom, if I try to plug in 0, we're dividing by 0. So this is where a lot of our algebra work is going to come in a little bit. So again, this is more like the background. I'm building up to what's going to be our final definition in just a moment. Where do we actually get all these values from? We're actually just going to remember one final definition. These are all kind of like intermediate steps to get there. All right, so let me go ahead. I might skip a couple of slides to go to the definition. Don't worry about that. So just to recap on what we looked at here. For a linear function, so lines, I use 2 points. I can get slope. That's what y'all learned in algebra. My first definition I gave y'all was, what if I use a comma f of a, x comma f of x? Then we have essentially still the same formula, y2 minus y1 over x2 minus x1, and then the limit for the instantaneous. And I have essentially the same thing here for the alternative definition. What we're going to do is we're actually going to focus on this last row here. It's going to be our main focus. Yes.
If they're all the same thing, essentially, what's the point of telling us all? Are there different use cases for them, or is it?
So we're going to see, we're pretty much almost always going to use the bottom one. Like I said, going from here to here was more like intermediate steps to show how is it derived. But there are some uses here still, because sometimes it might be easier to start off and simplify a function that looks like this rather than what we have down here. But we're going to focus on the bottom definition for the most part. All right, so we did all of this build-up work to see our next definition. Let's see if I timed this correctly or not. Hopefully I have the next one as a definition. This all gives us our definition we're aiming for. The derivative of a function, f, at a. Here we denote it f prime of a. Again, this is f prime of a. And we can use either definition. But again, we're mainly going to focus on the second one over here on the right. In fact, if you only want to write one, let's use the right definition because that's the one we'll see more often. F prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. We have this here. We have finally introduced what looks like to be the derivative and the notation f prime. And we can also make some quick conclusions here from this definition. This expression right here, we saw in the previous slide. Before, I said that that was the slope of the tangent line, or in other words, the instantaneous rate of change. But I'm also calling that the derivative at a. The inference I can make here is the derivative at a point is the slope of a tangent line at that point. So again, the derivative at a point is the slope of the tangent line at that point. We saw that because we defined this to be the slope of the tangent line, and now we're defining it also to be the derivative at the point. So all of that build up in background derivations and renaming our variables to end up here. I like to put both these definitions because some books prefer the left one, but then for the most part, almost every book I've seen nowadays uses the right one. I just wanted to include the left one in case you're looking at particularly an older book, but they are technically still the same definition in the long run. I'll give y'all some time to copy this. And then we're going to do an example in just a moment, where I'm going to say, find the derivative of a function at some given x value, or some given point. I also want to take a moment here. If you have taken calculus before, which I know several of y'all have before, right now we do not know the existence of any of those special derivative rules. We don't know if power rule exists yet. If you haven't taken calculus, forget you even heard those words. They don't exist. We'll actually prove that rule, I think probably tomorrow. We're going to prove why it's true, and then we'll be able to use it. We got to see why these rules actually do work whenever we get through it. All right, so let's go ahead. Again, if I time this correctly, let's go to our example. This is my note that this is still the tangent line. One other definition, apparently I forgot about this, that was going to pop up. If you ever hear me say the word a function is differentiable, it just means we can find a derivative, or in this case, the limit does exist. Not exactly, because we've done limits where they don't exist, right? So we can also make that inference. If the limit does not exist, then we say the function is not differentiable. So a lot of times you're going to hear me throw out the word in the future, differentiate this function, or find the derivative. That'll mean the same thing, find f prime of the function. Notice here that so far we're only doing the derivative at a point. We're not doing the derivative of a function, not just yet. All right, so now let's see if I time this correctly. Perfect. Using this limit definition of the derivative, let's get f prime of a if I have this function, and if I'm using a is equal to -2. Once again, I'll give you some time to copy this. We've got to get through the tedious work of going through all this algebra before we can get to our nice, quick method down the road. So just for convenience, I am going to rewrite that definition that I had earlier, which was f prime of a is the limit. Let's use the h definition. As h goes to 0 of f of a plus h minus all over h. So in this case, we know what a is. What's a again? -2. I want f prime of -2. So again, just for notes, I'm going to fill in for a. The limit as h goes to 0 of f of -2 plus h minus f of -2 all over h. So all I did here is instead of a, I put in -2. So somehow I have to evaluate this special limit. So I'm going to do some side work here so that we're not trying to do all this in a single line. Let's start off with focusing on, it looks like the top is where all of our work really is here. Let's focus on this here for now. F of -2 plus h. Again, I'm doing this on the side so that we don't have it all mixed up here. How do I get f of -2 plus h? What does that even mean for us in the context of this problem? How do I get f of -2 plus h? Not that we're going to plug in 0, not necessarily yet. If I gave you a function that said, give me f of 5, what would you do? You would plug in 5. So here, yes, so for f of -2 plus h, we're going to plug in not just -2, we're going to plug in -2 plus h. Yes, so we're going to write this. What is this? 3 times -2 plus h squared plus 3 times -2 plus h. So all I did was replace that x with -2 plus h. Because that's all a function is, it's a placeholder. Whatever I put in those parentheses, I replace the x with whatever's in there. All right, and now we have to go through the grueling task of cleaning that up. So this is where I say algebra skills might come in handy, cleaning up all of this. And this is also why I did it on the side, so that we don't have to write limit over and over again. So I have 3. How do I clean up -2 plus h squared? What do I have to do? Yeah, so we have to multiply -2 plus h times -2 plus h. One thing that we want to be careful about is that we're not just going to do -2 squared plus h squared, because we're doing a binomial times a binomial. In other words, we're doing our foiling deal. So remember this right here, that's -2 plus h times -2 plus h. We're going to multiply that out. So multiplying this out, I should get, what, 4 minus 4h plus h squared. I would agree. Again, multiplying it out, foiling, if you want to use that term, we get this here. -2 times -2, we get 4. -2 times h plus -2 times h, we get -4h. And then h times h, we get h squared. Plus, let's go ahead and multiply this out. 3 times -2. And then plus, we're almost done cleaning this up. What's the last thing? What's not the last thing, but what's the next thing I'd probably do? Yeah, let's distribute this 3. 3 times 4, we get 12. Minus 6 plus 3h. And is there anything left I can do to clean this up, if any? Yes. So let's just put it in descending order, just so that we have everything in order. Starting with the h squared. 3h squared. Let's see. Yes, minus 9h minus 6. So again, cleaning up through a lot of algebra, this is f of -2 plus h. In other words, what I highlighted right there on the left, that's what we have here. So let's put that back in. But before I do that, any questions about how I got f of -2 plus h? A lot of algebra moving around. -6. So from, it looks like we're getting it from right here, this -6. Oh, let me fix that. Good catch. Plus 6. Good example about how easy it is to actually make a mistake here as well. All right, so now that we can go back here, we have the limit as h goes to 0. What I have highlighted, f of -2 plus h, that's this over here. So I've got 3h squared minus 9h plus 6. Minus, what's f of negative 2? How do I get that first off? Yeah, f of negative 2, it's the same principle, right? I have f of x, I can plug in negative 2. Let's see, do I have any space here? Let's write this in orange. So again, if you want to write this on the side, you can. F of negative 2, that is 3 times negative 2 squared plus 3 times negative 2. It's an ugly looking 2. What does that clean up into if I do all of this? Let's see, negative 2 squared times 3. So 12 minus 6. I think we should get 6 if we do all of our calculations. So f of negative 2, that's 6. All, emphasis on all over h. So the good news is that we've gone past the worst part. If I did this correctly, we should be noticing something will occur. Again, I'm going to take a pause here. Then everyone see how I got here. Yes, we will eventually end up there. All right, does anyone still need to copy the right side? I can't really move this one up because it's not the same whiteboard. So I'm going to delete this right side over here. Let's see if I can do this efficiently. I cannot. So I want to keep the left side up just so that I can continue to use it. All right, so let's see what happens whenever I now try to simplify that expression. What's the first thing we notice that does some cleanup work? Yeah, so if I look here on the top, the first thing I'm noticing is I can get rid of these parentheses, and I end up with 6 minus 6. So I can see that these will go away. 6 minus 6. And while I'm at it, I know that the h on the bottom is giving me an issue. So I know somehow I want to get rid of it. One thing that might be useful for me in getting rid of that is I notice on the top, I can take out an h from the remainder up here. That is, I could write this as h times 3h minus 9. Again, I'm going to take a pause there. I factored out an h from the top. I know that I can do this, and I know I don't want this to happen because it's going to be really convenient in a second. What happens from here? Exactly. My h on the top cancels with this h on the bottom. And I'm going to preemptively answer one question in a moment. This leaves me with 3h minus 9. So again, another quick pause. One common question is, well, can I just have recognized that each of these terms has an h and then do the cancellation from there? Yes, it's just the same thing as what I wrote up there on the top right, but in your head. Again, I'm just writing out all these steps primarily for notes. All right, so now I have the limit as h approaches 0 of 3h minus 9. What now? Plug in 0 for h, because I got rid of the h on the bottom, which was the big issue. What happens if I plug in 0 for h? Yes, we get negative 9. So we did all of this work to say that f prime of negative 2 is negative 9. So the question is, now I found negative 9. That's great. I found a number. What does that even mean for us to say that f prime of -2 is -9? Yeah. So if I had this graph up and I drew a tangent line at -2, the slope would be -9. There's another inference I can do about that. For a line that has a slope of -9, is that going down or up? It's going downwards, right? Negative slope is typically going down. We can actually make one more inference here and say at -2, my function is decreasing. So at -2, my function is going downwards, is what I expect to happen, because the slope is negative. So one thing you're going to notice I'm going to say throughout a ton of the semester is I'm going to use the word slope, derivative, and rate of change essentially interchangeably. In fact, we can think of the derivative as just a generalization of slope. The derivative is the slope, but for any function that we're allowed to draw. Whereas the slope, we often use that to say the slope for a line. So we're no longer working with straight lines. We can work with any general function, assuming the limit does exist. One thing I'll mention about this is that it was not a coincidence that I got a lot of cancellation. In fact, we'll see if I'm doing this correctly in general, I should expect a ton of cancellation and cleanup. It was not a coincidence that 6 minus 6 was here, and then I could take out an h. If I did it correctly, I should be expecting cancellation of constants and then being able to factor out an h. All right, so all that work to just go ahead and find the derivative at a point. What we're going to do tomorrow is finding the derivative as a function. What if I don't want a single point? What if I just want to do it for any point in general? That is, what if I want f prime of x instead of f prime of 4, f prime of 8? What if I want a function where I can just plug it in and be done with it? Last thing I'll note here is, right now we're doing a lot of steps. Probably by Monday next week, we're going to learn that all this work, we're going to be able to do it instantly. Quickly through what we're going to call later the power rule, product rule, quotient rule, and like 30 other different derivative rules that we go through. I'm not thinking so, because this one's more of a test of algebra rather than more of a calculus question. Right now, this is primarily just to build up where does the derivative actually come from, and not something we just pull out of thin air. All right, besides that, that's all for today. I'll see y'all tomorrow. And I can see that slowly our days are getting darker at 6 p.m.